Well, hello everybody, and welcome to another live stream of NeuralMarketTrends.com. I'm your host, Thomas Ott, and we're here today to continue to talk about how to use RapidMiner for all your fun data science, machine learning, text processing, and whatever you need to do into the magical world of data and data mining. So let's get started. So today I want to talk to you a little bit about redoing a video that I've done before about balancing data. The video that I had previously, people have complained that the microphone was very low, and it was. My apologies for that. So we're going to talk a little bit about that today. We're going to talk a little bit about balancing data, about different classes, and then we're going to use a decision tree. We're going to talk a little bit about decision tree building. The reason why is that a lot of line of business managers and a lot of people in general understand the concept of decision trees. They really get it. It's a very visual type of algorithm that lets you follow down these branches of a tree to get to the leaves or the output and go from there to figure out what you're doing. Typically used in classification types of situations like churn, loyal, male, female, something along that line. But it's also can be used for numerical data too. And one of the new enhancements in RapidMiner 8 is a updated decision tree algorithm that lets you actually do numerical labels as well. So let's go ahead and let's try to share my desktop here. And let's talk about what we're going to do today. Okay, I have loaded up RapidMiner here already. I'm currently running version 8.2. And I'm going to load in some demo data that we used, actually that Ingo Mariswa, the founder, one of the founders of RapidMiner, used for his click integration demo. If you go onto the RapidMiner YouTube channel, and what I'll do is I'll post a link to it probably either now or at the end of the video, you can see on how you can actually use Click and as well as Tableau if you want to, and how you can integrate that with RapidMiner so you can do all your data analytics in RapidMiner and push it into production and use a Click dashboard. Really, really cool. But we're going to use the demo data for that. And we're going to talk a little bit about class size, and we're going to talk a little bit about how to build a decision tree for all you people out there. Okay, so I have it right here. I have some raw data. I'm going to drag the raw data in, and I'm going to wire it out. I'm going to review it. Over here, clean this up. I'm going to wire it out, and I'm going to inspect it first. Okay, and we're going to see what's in it. So we hit the run button. And you can see here I got 4793, 4,783 examples, also known as rows. One special attribute, which is also a column, special column, which in this case is blue, which means it's an ID. It makes sense because we have a customer ID. We have 13 regular attributes. These are currently being used as the inputs into a model. Very, very raw data, and it looks a lot like a spreadsheet. So let's go take a look at the descriptive statistics tab. Also very, very handy and important to use here as you begin to drill down in your data before you do any type of machine learning or data science or anything like that. It's a wonderful way to dig through the data and see what you got. Okay, customer ID is currently listed as a real number. The state is a polynomial, which is a string value. You can see here, if you click on this, we have a lot of entries from Florida. And the least entry state is looks to be, I guess, Nebraska. Come down here, and these are some mobile phone information. I guess these are some minutes on how many people have spoken, whether they're using a mobile or a landline, age, some sort of pack that they're trying to use or they've been sold to, limited service, and churn status and gender. And one thing you notice over here is under churn status, it's also polynomial. We have 435 people who have churned and 3,400 people who have not churned. But we also have 958 missing columns or missing entries. So in this particular example, those missing people or those missing entries don't have a churn label, don't have a either they churned or are still loyal. And those are the people that we're going to pretend are going to be the ones that we want to score against and see, hey, can these people can we predict if those people are going to churn or remain loyal to us? And of course we have male and female. And we take a look at this just by this little visualization chart here. We can see that that's fairly balanced, but the churn status is not balanced. And this is where the sampling and this is where balancing the data is going to come in. So why is that important? Let's go back here and let's just, for the sake of it, attach a set role. We want to determine the churn. First, what we're going to do is we're going to filter out. We're going to take what we're going to do is we're going to filter out the people who have already been churned and who have already been loyal. We're going to say whoever's not missing for your churn status will be the ones we're going to use for just a quick model. We're just going to do a very quick model. And then we're going to set that column, which happens to be churn status, as our label. Now, I may have talked about this in the earlier live streams, but RapidMiner, when we go back to the data here, let's take a look at the data here real quick. We talked about regular attributes, and a regular attribute is really a regular set of columns. They are just meant to be input to the data into the model. If you want to specifically tell a column in RapidMiner, tell a machine learning algorithm like a decision tree or something else to learn the patterns in that column, you have to create a special attribute. And you see here, there's already one special attribute, the customer ID. This special attribute tells RapidMiner this is a customer ID. It's a key. Don't use it in any modeling. Don't use it at all in any modeling. Just pass it through, and you may be able to use it later on downstream to sync up with some other database or something along the line. So what we're going to do is we're going to do two things. We're going to filter this column. I'm going to drag this one over here real quick. We're going to filter out this column to say, just for now, just put aside all the missing ones, the ones with the question marks, and just select all the ones that are filled out and actually have a set role, or we're going to apply it as a label. And in RapidMiner, a label says, this is my target output variable. This is what I want the machine learning algorithm to learn. So the way we do that is using a set role operator. You can see here. So now let's go run this. And you'll see now I've already reduced the data set. It was 4395, I believe it was. Now it's down to 3835. So we lost about a little bit over 1,000, I believe, example rows that are going to be used later on for scoring. And you can see here now the churn status has changed to green. And so if I click on statistics here, you'll see that now it's saying it's a label and customer ID is an ID. Perfect. Now, let's just go ahead and drag a decision tree in. This is normally what people would want to do. They're going to say, hey guys, I figured out my target output variable and I got my data and I want to throw something on the wall and see what the decision tree says will stick, right? That's typically what you hear. And you can't be further off than saying that because it's plain wrong. Okay, let's just drag a decision tree and I'll show you exactly what I mean. Let's not worry about the parameters for this very moment. We'll talk a little bit about them later. But we're going to run this. And now we're left with a beautiful one node decision tree. It just says loyal. It doesn't say a darn thing. I mean, it's completely useless in this particular case. And the reason why it's useless is because we have an unbalanced data set. Remember, right a few minutes ago, I talked about that churn, the loyal and churn. If we look at this, click over here, we can see that we have more loyal customers than churn customers. And if I went back to looking at what that model was, if I just run this again here, you could see that it automatically assumes everything is loyal. So what's happening is the model is generalizing over all the data and says, so you may have one or two, or you may have 340 people who have churned. Well, I'm looking at this as just them being loyal. So that's not the model that you want. So if you threw this up on the wall and it came back and said this, you're going to get the wrong answer. So how do we create a balanced data set to actually give us a decision tree that makes more sense? Okay, let's go do that now. So in RapidMiner, there are multiple different ways to handle sampling. There's upsampling and there's downsampling. We're going to do an initial downsample, and we may touch a little bit using the smote upsampling operator in a short while here if we have some time. But what we're going to do for now is we're going to take those 340. Now let's come over here. 435 churn candidates, and we're going to take this class, the loyal class, and bring it down to 435. So there's going to be an equal amount of churn and loyal, and we're going to run it through the decision tree, and we're going to see if the decision tree can come up with a model that makes more sense, a model that that says, hey, are there differences between loyal and are there differences between churn that I can pick out if the classes are relatively the same? Okay, so we're going to use a sample operator for that. RapidMiner, like I said, here's a bunch of different sampling operators. We'll talk a little bit about them a little bit later. We'll just drag in the very simple sample operator. And here we can just say, hey guys, we just want to just take an absolute number of samples, 100. We could do that, but it's not balancing it. So if I did that and run that again, I'm going to still have the same data set. But what I want to do is, or the same result, but what I want to do is I actually want to toggle on balanced data. So here's where I actually have to manually input the data classes or the classes and how much I want of each. Okay. This is the very low level way of doing it. And I'll show you a really cool way to do it in a few minutes using nothing but macros. Okay. So I come over here, I toggle on balanced data and I go to edit list and I type in the churn class, not churn, and I want to say 435. Come here and I do the loyal class and I say 435. Hit apply, and if I do a breakpoint here and we run it, we should now have a total of 870, right? 435 times 2 example rows, and if I click on statistics, they look like they're perfectly balanced. Wonderful. Now, let's go run it through the decision tree and see what happens. Okay, we actually get a slightly different decision tree that may or may not make sense here. Okay, it's saying that the most important splitting attribute is mobile 2014. So if you were using the mobile 2014 by more than 13.57 minutes, maybe, and you used a landline less than 73 minutes, you are probably going to be churning. It's predicting it's churning, but it appears, if I click on this, that there might be something going on here. I have an equal set of classes here. If I look at this very carefully, this decision tree is maybe not a really good one because by looking at this thickness here, the blue and the red, it's saying that the majority of the classes are dropped into the churn column, and only a very few, this very thin line, are being dropped into this loyal column. So we still have a way to go with our decision tree here. We still have a way to go, and we may end up finding out that the decision tree may not be the best model, but that's perhaps for another video here. So what else can we do? What else can we do to actually figure out how we can test, we only have a small data set. How can we test more data and figure out how we can actually determine the performance of this model? How good is this model going to be in the wild once we actually put real scoring data to it? Okay. Well, the one way to do that is through using a decision tree. Okay. Now, I'm sorry, not using decision tree, you're using cross-validation. So let's go build a cross-validation operator. I'm going to just disable this for now. And I'm going to come here, right click, and I'm going to import a building block that uses nominal cross-validation. It happens to have a decision tree already built into it. So we're just going to do that. Now, I'm showing you the wrong way over here. The sample operator is eventually going to be put into the cross-validation operator. And I'll talk a little bit about why that's important. But right now what I'm doing is I'm kind of contaminating the data. I'm not really making an honest evaluation here. So let me just get rid of this and we'll run it. Let's see if we can output the performance here. And it still comes up the same. And let's look at my performance vector here. And this is perhaps how you, as a line of business manager, and even as a data scientist, well, as a data scientist, you'll be doing this anyway, but as a line of business manager, you might want to understand what a confusion matrix is if you're using some sort of classification problem. Okay, what I have here is that I have a model that is turning out that's only 50% accurate, which is terrible. It's telling me that it's a coin flip essentially. It is very good at predicting churn, okay, but it's not very good at predicting loyal. And if I look at my area under the curve, I mean, it's exactly like a coin flip. So it doesn't matter. You will be better off. Well, you can guess, and you'll probably still get the same right answer every time. So this is not a model that you want to use for production. Let's just see if there's a way we can actually get more performance out of it. Okay. Let's just see how we can actually, if we really want to use a decision tree, how we can actually get more performance out of it. Let's go back to design. Now, I've already pre-sampled the data before I fed it into here. And that's probably not the right way to do. Remember, if I came here, if I did a breakpoint here, and I did a breakpoint here, let's run it again. And I have now, before I sample, I have 3,835 example rows. That's a lot of data. And then when I go down and I sample it down, I'm only left with 870. So I took a huge cut in data. I mean, what happens? How do I know that, we didn't randomly select the wrong loyal category ones? Maybe, there was other information in the data set that we just lost by randomness of sampling. I mean, it could happen. So how do we actually use this to our benefit? How can we actually use the different loyal and churn candidates to our own benefit here? Okay. Well, what we're gonna have to do is we're gonna have to put the sample operator inside the cross-validation operator. And I'll tell you what happens why. So we're gonna cut this, and we're gonna reconnect. And now we're gonna just take this and we're gonna just say, hey, paste this here and connect them. Now, what's going on here? Now, if you watch any of the RapidMiner videos on cross-validation that Ingo has done, you'll go into depth about why we're doing these things, about not contaminating the data. There's a fantastic write-up on the blog, a four-page mini-series, blog series, as well as, I think, a white paper that goes into heavy depth of this, about why we start embedding sample operators and different pre-processing operators inside the training side, so that we try to do an honest evaluation and we don't do contamination of data. We don't do data snooping, or we don't do data leakage into the test set and the training set. So there's a whole great set of articles on there. I highly recommend that you check those out. But what's happening here is that in the cross-validation operator, we randomly break up the data into 10 sets. We train on one set, test against the other 9, and then we iterate. Then we select another training set out of the 10, train on that, and test on the other one. So what's happening here every time is, when we sample, we always take the 435 churn candidates, but we're also then randomly selecting 435 loyal candidates at the same time. And we iterate over this 10 times, and then we build a model from that. Okay, so let's go see. Let's go pause this, and let's go run out to see if we actually have a better result. Okay, looks like the same tree, but now we're starting to get a slightly different accuracy, and it's still not that great. Now we have an accuracy of 87.46. We're very good at picking out loyal, but we're not very good at picking out churn. So this is telling me that the decision tree is a very bad model probably to use here. Let's just see if we can do any other thing to try to squeeze out some better performance here. So let's take a look at this. We're going to do automatic. Let's try to run it again. And we should probably have the same results, which we do. Terrible at picking out churn. And now let's go try something different. Let's go try a different algorithm. Let's try working with the parameters. No good there. So just so you know, you can change the different splitting criteria. Let's talk a little bit about these parameters here. So there's multiple different types of ways to split your tree here, and the default is gain ratio. I think gain ratio is probably a very good default, but you can definitely try other ones. And if you don't know what they mean, if you click on the little eye here, it'll tell you what all those different algorithms do. Like, information gain calculates the entropy of all the attributes, and then the one that has the least entropy is selected for split, and that typically means that the one who has got the largest attribute typically gets split, which kind of is a bias. The gain ratio tries to adjust for all that, so it's a little bit more honest in my opinion. So gain ratio is probably a good way to get started if you want to, but there's also a bunch of other parameters here that we can talk about. The maximal depth. How deep do you want your tree? Now remember, a decision tree is really an upside down tree. Okay. The leaves are at the very lowest level. So this is telling me that for, I want to build a tree that has a maximum depth of 20. Okay. And as it's building this tree, it's got to split and it's got to do a bunch of other different things. Like it has nodes. So the splitting is on a node. So if I come over here, let me look at this. We're not going to use that one. Let me go try this one again here. So this is a node, right? I'm sorry, no, this is a node. This line is a node. So it splits, and this is a leaf, right? So this is how RapidMiner, and this is how typically you evaluate decision trees. This is how they are. So this is a leaf, and these are the specific nodes and how you split and so forth. So now how do you actually determine the splits? Well, that's where these parameters come in over here. So if we actually, and we'll talk about pruning in a second here. So pruning is actually very important. So as a tree is being built, it's going to it's going to apply its splitting criteria, and it's going to say, well, maybe this branch over here only has 3 example rows that it applies to. So like if I come back over here and I say, see, this is a very, very thin, very, very thin branch. So I might not really want to create this branch. I might want to lump this into maybe this branch, or force the decision tree algorithm to say, hey, if there's only 3 examples out of 3,000 that cause this to split, this is not really what I want to see. I want to prune that branch. I want to only have thick and healthy branches. Like if you look at this one here, this is a very thick and healthy branch right here. Okay, so what you can do is you can come over here to the parameters. You can apply pruning and you can apply pre-pruning. Pre-pruning happens as the model is being built, and pruning happens after the model is built. Okay, and the way you do the pruning is by setting these parameters here. Like this is the after the tree is built pruning. So, and typically the 0.25 is pretty high. You can say we'll set this to 0.1. And the gain and the leaf size over here and the minimal sizes are happen as the tree is being built. So what this is saying is that in this particular step, I need to have at least 4 examples to create a split, right? To create a branch. And I need to have a minimum of 2 examples in that leaf. So I can change this to say 4, and I can change this to say maybe 10. Let's just do 10 and 10. And if I run this again, now I get something different. I get a tree that doesn't seem to work, right? If I come back here now and I say, well, let's go do 2 and 2, I should get a different tree. Well, looks like it's the same tree. In this particular case, it's the same tree. But let's just see what the performance is. Performance is still pretty bad. So why don't we try something else? Why don't we actually try some hyper tuning, some hyperparameter optimizations, and see if we can squeeze anything else out of this? And if that's not the case, why don't we try a random forest afterwards? Okay. So how do we actually tune the various parameters here? Let's go do this. We'll get optimize parameters. And we're going to copy this. We're going to cut this. I'm going to attach it into here. And we're going to output the performance because that's what it wants to do. And now we're going to edit the parameters. So we're going to say, take a decision tree. We're going to change the depth. Maybe we're going to go from 2 to 10. Confidence, we want to say, I'm going to say select the confidence. We're going to say 0.1 to 0.5, and we're going to do 5 steps. I forgot how much we did the maximal depth. Okay. And let's just see here. Let's do minimal gain. Minimal gain was, let's go from 0.1 to 1 and 10 combinations. And let's give that a try. And we're going to output the performance, and we're going to output the parameters, and maybe we'll output the model if it gives us that. Let's go output the model here. There we go. Okay. Now let's run this again. Now, while this is running, we can take a look at what the optimized parameter grid is doing. It's saying, okay, well, it's giving us, but remember, the accuracy in itself was not really giving us what we want. So we're going to tell the hyper tuning parameter we're going to talk. Let me back up. We're going to tell the parameter, the optimization parameters, to select a specific performance criteria, and we're going to optimize around that. So this is still not what we want. I think ultimately what we want is we want to be able to see here. This is terrible. We actually have a very terrible, terrible thing. What we want to do is we want to be able to provide a better area under the curve. We're going to try to see if we can pull out the loyal candidates a little bit better. I'm sorry, pull out the churn candidates a little bit better. So let's go back over here. Let's double click on this. Double click on this. And what we're going to do is we're going to get rid of this guy. And we're going to get a classification performance operator, perf. Don't mind my dogs. They are being crazy. Let's go do binomial. I'm sorry, binomial. Come over here, and we want to optimize under area under the curve. And this may not like it. Let's see here. Oh, yes, performance. What did I do? Disconnect. So I need to go ahead. Let me double check this here. Okay, that seems to be running. And we are now optimizing for area under the curve. Now this has changed from accuracy now to area under the curve. And you could see here that I'm not getting a very good area under the curve. So decision tree may not be the right way to go here. Let's go take a look at our performance operator. Still not good. I'm still a coin flip. So what do you do now? Right? I started this video off saying, oh, let's go talk about decision trees. But sometimes decision trees are not the right answer. Sometimes decision trees are not the right machine learning algorithm. And this is why you need to test multiple different models. In some cases, you may need to do a model bake-off. Okay? So how can you actually try to do a model bake-off without going through all these steps? First, I mean, you should definitely always optimize. But let's go look at comparing the ROCs here. I'm going to do an automatic sampling, okay? And we're going to take that decision tree and we're going to put that one back in. This time we're going to use maybe a random forest tree. Connect those in and let's try neural net. Do a deep learning just for the heck of it. We're going to test and we're going to see how good these are. This is just a first step. You don't necessarily have to do this, but this is just something I would do to see if I see any differences by using the different algorithms just quickly and visually, and help me narrow down what I want to, what's the word for it, focus on. While that's running, I'm going to actually check to see if there are any comments here by not sharing. And there are no comments. Excellent. Let's go back to sharing. And it looks like I have some, oh, I forgot to output this. Let's go just look at this. So it looks like deep learning is not that good. And random forest, okay, all right. Let's go try it. That's right, I'm not using the sample operator. Look at that, look at that. It's Gen 2. All right, let's go try this here. All right, let's try that. Oop, no, let's go pause this. Let's go output this here real quick. Get rid of this guy here. We're just going to look at it visually. Let's just do the sample in there so we balance the classes. Aha, now this is a little bit better. This is a little bit better and a little bit different here. Still saying the decision tree is pretty good. Let's try a different one too as well here. Try our friend. Oops, an old neural net. Let's try our friend the KNN. Try our friend KNN. Everybody loves KNN. I'm going to do mixed measures. Okay, we're going to say 5. Okay, so KNN might be looking pretty good, but it still looks like it's a 50-50 chance here. So let's go try this. We're going to use a KNN. I'm going to get rid of this guy, disable him, put a KNN in. And we're going to optimize the K value. Going to optimize the K value. We don't got that anymore. We're going to go K. Boop. I'm going to say 1 to, I don't know, 20. Do it in 2 steps, or do it in 18 steps, 19 steps. And we're going to optimize area under the curve. So let's go see while this is running. So yeah, not that good. Still not that good, but it's beginning to look a little bit more like what I expect it to be. Let me close this out here. Okay, so we did that. So just slightly better than a coin flip. Still not the good model to do here. All right, let's go try. I forgot what he actually used here. Let's see what Ingo used. What did he actually use here? And we'll open that another time. Let's go see here. Let's go try naive Bayes. I'm just out of curiosity. Naive Bayes. Slightly better, but still not any good. Still not any good. All right, let's try this here. Oh, what am I doing here? Sorry, that's wrong. That's wrong. All right, a little bit better here. All right, that's what I was wrong. See, this is what happens. So let's go try this guy again. I think the K&N was really the one that actually does it. We may have to squeeze out some more performance somewhere else. Okay. Let's go try it and make a higher batch here. I'm going to say go from 2 to 100. 19 steps. All right, let's try that. Still not good. Still not good. All right. All right, so that's the case. Let's go do something else. Let's go try a new operator. Let's go do smote upsampling here. We may have downsampled too much. Over here. Smote real quick. Okay. Automatically detect. Okay, fine. Let's go see here. So now with smote upsampling, what it does, okay, now we have a balanced class. So with smote upsampling, what it does is it takes the data of the minority class, which happens to be the churn, and uses a k-nearest neighbor and tries to generate and create new points around what it thinks it should be and tries to then bring it up that way. So this is an upsampling. So in the one that we just did now, downsampling didn't seem to work at all. So let's go try this actually here. So we're going to cut this and we're going to put this inside the cross-validation. And we're going to see if it makes a difference. And what we're going to do is we're going to go back and we're going to use the old decision tree one that we first tried here. And we're going to try to optimize around that. So let's just see if we're going to do that. We're going to take this guy back and we're going to say decision tree. And let's just optimize for the depth for now. Okay, we're going to optimize for the depth. Okay, and we're going to hit run. Okay, so now it's running. It might be taking a little bit of time. Actually, I'm going to disable the enable parallel prong. Okay, let's go try this again. Okay. Still optimizing on the area under the curve. We'll see how this goes. Things are not looking so good. Let's try this. Stop this for a moment. Here's the stuff that you got to do all the time. Let's go see here. Excuse me. Confidence and minimal gain. Okay, let's run this again. And while this is running, I'm going to stop sharing my screen. And I'm going to see if there's any more questions. Okay, seeing none, that's okay. And then we're going to share the screen again. And now it's taking a little bit slower. And while this is running, I'm going to pause the screen share. And it's taking quite some time. Which is okay. Boy, oh boy, oh boy. This is turning out to be a pretty rough data set after all. We're going to maybe have to do some other work to it. We're going to have to definitely do some other work to it. We may have to end up doing some feature engineering here. Okay. Well, you could definitely see that it's taking a long time after toggling off the parallel execution boggle. But let's just see, and we're looking like we're definitely not making any improvement. Definitely not making any improvement in the area under the curve. So I'm going to stop this here, and I'm going to go ahead and try one more algorithm. One more algorithm. Okay. I'm going to try an SVM here. And what we're going to do is we're going to use a radial. And don't tell me you need to have everything. You're going to need to have everything in numerical, I think, right? So guess what? We're going to have to do a nom to numerical conversion. Ooh, this is getting crazy. Dummy coding group. Let's see if this works. Again, mirror. Oh, silly me. I need to go ahead and I need to toggle enable this parallel prosecution. Okay, let's go see if this works faster now. And if we actually get a better model. And if this takes a little bit of time, what I'm going to do is I will call off, or I will sign off for next week, and we'll pick it up then again. I don't want to waste anybody's time. We'll see here. And we're also, we should probably also do the, oh, we should do the default. Here we go. This is my bad here. Let's go try this. SVM, we're going to do gamma. We're going to do C. So this will be 0.01, 10, or to 100, logarithmic. I'm sorry, no, this is from 0 to 1,000 linear. And then gamma will be 0.1 to 100, let's just say in a log. Something like that. Let's just say that. Okay. Let's give it a try now. Why are you giving me an error here? Cannot handle a missing, but there is no missing. Nope, no missing. Perfect. Okay. Let's just see what happens. Let's see if we're actually going to get any results now. Or this will take a long time to optimize. Boy, what a rough live stream today, huh? Well, it must be the weekend. It must be Memorial Day. Well, this is obviously going to take a while. So since this is going to take a while, I'm going to actually stop sharing and I'm going to call it a day and wish everybody a fantastic holiday weekend. I hope you enjoyed this live stream because it's always fun. This is exactly what data scientists do, and this is what I do day in and day out. Sometimes things work out for you and sometimes they don't. So you got to kind of think outside the box and think about how you would actually try to solve this problem. So what I would do now after this is I'm going to let it run for a while, and if it doesn't do anything, I'm going to do two things. One, I'm going to maybe sample the data, just upsample it, but then take a random cross section of it and try to build a smaller model and work my way up there that way. Or try different algorithms. And if they still are not showing anything good as far as in a confusion matrix, what I would do is start looking at some feature engineering and see what can I add or what can I convert in the data set to make it a little bit better. These are all the typical things that you're going to do as a data scientist or a machine learning expert. You can't just throw stuff on the wall and see what sticks, especially as I showed you with my original decision tree. You have to always kind of think critically at each step. What are you doing? Am I reducing the data? Is that the right thing to do? Am I upsampling? Am I downsampling? How am I attacking it? All those different things you need to do on a day-to-day basis if you want to get into this field. So saying that, have a great weekend. This is Thomas out for neuralmarkettrends.com. I'm going to just stop sharing and check to see if there's any comments. And if not, have a great weekend. Okay, let's go see what we got here. Nothing going on. Guys, have a great weekend.